A warm good afternoon to all of you. Thanks to Varnatan for providing the instructions, and you can check it out the result of the previous webinar quiz through our social media platforms like UL Space Club's Instagram and Facebook page. I cordially invite all the scientists, veterans, teachers, UL Space Club organizers, students, and all other participants to the 23rd session of UL Space Club's webinar series. We, the UL Space Club, is a foundation under the umbrella of Uralanga Labour Cooperative Society, stands for enriching and flourishing the scientific aptitude of students, especially in space field. Within the 3 years from the starting, we conducted many great offline events that's before COVID. And from the beginning of this COVID pandemic era, we started this new venture called the webinar series, which is going extremely well for these past 6 months. Today, in the 23rd session, we have Sri Manish Baji as our lead speaker on the topic Nobel Not for Black Holes. I know that the first thing comes to your mind while hearing the title of the topic will be the 2020 Nobel Prize. And yeah, the Nobel Prize in Physics 2020 was divided, one half awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. The other half jointly to Reinhard Genzel and the woman Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. So many sessions in our webinar were related to the black holes, and enthusiasts may watch it from our YouTube channel after this talk. And our chief guest is the curator at Regional Science Center and Planetarium Calicut. He is very close to us, the UL Space Club. So it's my pleasure and privilege to welcome you, sir. Namaste, sir. After that, we have Varnatan, Abhinandatan, and all core team members here to give you the instructions when it's necessary. And moderator of the session, our Shajil sir, is here to control the session, and he will give the informations about our speaker. Our chief mentor, E.K. Kuti sir, the former director of ISRO, is here with us as always. And the whole webinar family, including the eminent scientists all over India, will be with us in this session too. UL Space Club student fellow, Master Bharat Srijit, will handle the Q&A session after the talk. Damodaran sir, the one who plays the major role in connecting us to UL, is here to express the word of thanks after the session. Our streamer, another student fellow, Adil Krishna, is also ready. So without any further delay, I welcome the moderator, Shajil sir, to take over the session. Over to you, sir.
Thank you, Sriram, and a warm welcome to all who gathered in this meeting. And we are sitting here for the 23 weeks. And we are celebrating the day also, and we are enjoying in this era of pandemic. And the US Space Club started in 2016, and most of the students who are entering this US Space Club is so curious about the space and all these things. And the first question they ask in the doubt, that will be about the facts. Now, in the last month, we hear that Roger Penrose and Reinhard Genzel and Andrea Ghez cleared the Nobel Prize for the related things with these black holes. And we are in search of a person and who is relevant with these facts. We need not worry about that thing, because for the 3 decades there is an institute in Calicut, Regional Science and Planetarium, that is nurturing the scientific minds and number of the community all over the northern area. And that institution is doing a great deal for the past 3 decades. Unfortunately, we have now with us and in Calicut, Manas Bagchi. He's from exactly from Bengal and Calcutta, and he is there still guiding and leading that scientific institute of politics. And he is so interested in nurturing the students to the world of science. And when he invited him, he was very happily received that invitation from our chief mentor, E.K. Kuti sir, because he is also part of this Regional Science Center is continuously supporting US Space Club for the past few years. And definitely he is with us, and Today morning, I had a live session with him. Then I asked a funny question with him. How many of the number of students, number of books totally read? That was my question to him, and he made a note and replied that I couldn't count it because we have heard a lot of speeches from his part, and all these speeches delivered that with wide reading and his quest for new knowledge. That's why he selected the new topic that is never ever discussed in these kind of forums in Kerala. I think so. The Nobel Award for Mathematics. Now we have the exact person with us. He's so curious now and so interested in nurturing our students. And today we have with us E.K. Kuti sir, our mentor, and continuously we are getting support from the people scientists from ISR for the past 22 weeks. And we have teachers, students, and large community of students are watching this webinar through YouTube. And it's recorded the, let's say, ever pressure for our students. And I formally introduced to this forum our presenter, Manas Bagdi sir. Manas Bagdi is a curator of physics and computer systems and presently heading the Regional Science Center Planetarium, Calicut, under the National Council of Science Museum, an autonomous science organization of the Ministry of Culture, Government of India, as a project coordinator. Besides working towards technology development for the museums, Manas has curated several topical galleries. He has curated exhibitions and galleries on space science and astronomy, with the nuclear power, oil, natural gas, genomics, energy, water, etc. For his current assignment, he was the head of computer division of the Penrose Research and Training Laboratory, the research and development wing of NCSR. He was instrumental in the development of National Museum of Indian Cinema and Virtual Experiential Museum in Varanasi, which was project initiated and monitored by Honorable Prime Minister of India. He has developed several technologies like 3D stereoscopic video editing and playing units, automated stop motion animation development system, seamless visual speaker, etc. Besides technology development for the museums, he has keen interest in social recognition of various science and technology innovations. He was contributing editor in the Time Supplement, the Indian Daily, the Telegraph and Article, published from Kolkata. He has published a number of papers, obtained one patent, and he has applied for 3 patents, which are patent pending stage. This profile reveals that he is an all-rounder. He knows cinema, he is not literature, he is continuously searching for science, and we can call him. He's a real scientist, and he is nurturing the students and the whole community. So we are so proud to be with you in Calicut. You are proud of Calicut now, and we make a warm welcome to this forum. Sir, welcome. And I welcome all the students and our veterans and the scientists from ISRO to the forum. And again, I invite Manas Bagdi sir to present the interesting outcomes.
Thank you so much. And I'm really humbled by the kind introduction that you have provided. Even though I think it's a little too much for me, a little too heavy heap of praise that probably I don't deserve. But anyway, I'll just make my presentation ready. I'll share my screen with you and start my presentation. Just allow me some time because in course of this presentation, I will present, probably I'll refer to a few videos, I'll read out a few things. So please allow some time. Just a minute. Am I audible and visible?
Yes, sir. Your presentation is coming and you are available. Okay, sir. Only request to the participants, sir, don't try to present your part. That's a request to the participants from our from the part of
Is it full
oxygen.
screen now? Is it full screen now? Is it visible full screen?
No, it's presenting. It's not. It hasn't come. No, sir. You are presenting is seen now. I think
But the presentation has not come yet.
has not come. Has not.
It is visible.
It is visible. It is visible.
And is it full
Sajil
screen?
Marsh.
And is it full screen?
Yeah, full screen. Yeah, full
Yes,
screen.
it's visible. It's visible. That's a mistake from my.
Full screen visible.
I pinned.
Okay, thank you. So today's topic, we decided to have a discussion with Putti Saab and Sajil Saab that we will discuss the Nobel Nod for black holes. Now, it is very interesting to choose this topic because black holes have become a cultural icon almost. It is like the unicorn and the gargoyle who resides in the realm of scientific fictions more and in cultural domain rather than in the experimental reality of the world, it seems. And very recently in one of his lectures, Professor Reinhard Grenzel, he started and addressed the audience with this opening remark that everybody seems to know everything about the black holes because we have seen a lot of sci-fi movies and we have read a lot of popular science books. And then he stopped a little and continued, we must understand it from the experimental point of view. And that is why I wish to give you a little different picture of the black hole. And while talking about the black holes, I wish to diverse a little and delve into some other related connected issues to show that astronomy to me is very interesting, and I of course think that it is the same to almost all of you because you are pursuing this interest for quite long. And that is because there's a very interesting mix in astronomy. Astronomy is a subject in which first you observe something, you theorize it, you try to explain what you see, and then you understand that you have limitations of observations. Initially, when it started, only the naked eye was the instrument with which we had to explore the universe. But then, in 1609, Galileo trained his telescope towards the sky, and world was never the same again because he changed the models and others theorized as well. And then we understood that the limits of our vision has been pushed quite a lot by Galileo. We had telescope. And then we understood that the new things, those are coming, are not fitting into our existing theories. So it was theorized, and further instrumentation like spectroscopy and other things came up, and slowly it snowballed into a huge revolution. I wanted to just cast the light on this issue that astronomy is a science that is very heavily dependent upon various types of technology inventions, technology innovations, and particularly instrumentation. And in that, black holes have almost become the pinnacle of it as from theorization point of view and also from the experimental aspects. I would like to intensely point out to the experimental aspects, and that will come in course of time. But of course, we will also discuss a little bit of theory and concepts because those are important ideas as well to explain the universe as it is. Now, black hole is an idea which is like every revolutionary idea. It is said about revolutionary ideas that firstly they are ridiculed, then they are opposed, and then they are considered as self-evident as if they were always there. Black holes also were somewhat like that. Initially it was very heavily ridiculed, then people opposed it, they said it cannot be true, and then finally now it appears as if it is everywhere. And maybe this acceptance of this whole concept is based upon certain experimental findings which started from 1960s, but actually we can think of 10th April 2019 as a landmark day when we got the image of the black hole to show that yes, it is something real from the experimental world, and it comes from the mathematical constructs of the papers right down into our reality of universe. Now, while doing so, I'd like to go a little fringe-wise. Not only in 2020 black hole has been rewarded, and the Nobel was awarded to the development of black holes and associated things, but in 2019 also we got something interesting. But before going to that, we have an idea, we have a set mindset about the black holes. It is almost like looking towards the Niagara, as if we all know that we are safely standing behind the rigid and sturdy balconies, but we have a sense that somehow if one topples down, it can get into an enormous peril, and that will never end. That will end up everything will get squeezed and everything will go vanished. Yes, it is to some extent true, but to a large extent, there are many ideas in it which are not really verified that way. Like one example I'll give, the people sometimes think that it is actually a larking vacuum cleaner and it will suck up everything around. It's not true. Suppose we think of a situation where like probably Archimedes could have said, Archimedes said that give me a place to stand and a lever and I will lift the earth. The same way we can also claim perhaps that give me an appropriate mechanism to squeeze up everything within a short volume, within a small volume, and then we can create a black hole out of anything itself. It's true for sun, it's true for earth, but of course there are other issues. You have to forget the electron degeneracy, you have to forget the neutron degeneracy. We'll come to that at the appropriate moment and appropriate time. But to begin with this idea, what we have, this mental picture like Niagara, it is true, but not exactly. Suppose we convert the sun to a black hole. What will happen? Will it suck everything up right to the end of the solar system? It's not so. In fact, at Earth, we will not even have any idea, because a black hole, what remains after it forms the black hole is only its gravitational signature. Yes, of course, the light will not be there, and that is why probably the life will not exist as well, but things will not be sucked up. All the planets, they will go around the same center, the same way, because the gravitational signature will not change much that way. In 2019 that I was talking about, two things were awarded Nobel Prize. It was told that the origin of the universe and humanity's place within it was shared in the Nobel Prize spotlight, and it was also in two parts. One went to Peebles for theoretical discoveries in physical cosmology, and the other part went to two persons separately for the discovery of exoplanet orbiting a solar type star. But these are also representative of developments which are very strongly dependent upon instrumentation, dependent upon experimental data and verification, and there are definite innovations in it. I'd like to talk a little about it, because imaging any form of data acquisition and novel mechanisms are hallmarks of astronomy. So let us see what it was. But before that, it has already been discussed that Roger Penrose, Andrea Ghez, and Reinhard Genzel are the Nobel awardees for this year. We will come to their works very soon, but let us start with this particular invention. This was an antenna. It was almost an accidental discovery, you can say, but there were some plans behind it as well. As if in philosophy of science, sometimes it is said that you can get exactly what you are looking for. serendipities do not exist much, because you have to have an idea what you are actually looking for through an experiment. In 1964, two Bell Lab scientists, Arno Penzias and Robert Wilson, they were conducting experiments with Holmdel horn antenna, and it was a very sensitive device that was originally used for uh, uh, to collect the radio waves from bouncing off from eco balloon satellites, and later on Telstar satellite. They were using it, but they faced a very peculiar situation. This antenna, we will show how it works in a while. And there you can see that it can rotate 360 degrees in two planes. And that is why it can collect signals from every possible direction. And when it was collecting signals from every possible direction, it found that there is a constant background noise from whatever direction you point it to. And that was peculiar. It was not expected. They tried to exclude it. They tried to go very minutely with all possible options and exclude them one by one to find out whether it is something that is happening nearby. But they failed. It never occurred like that. And what happened is, we actually did not understand that we were looking at the first light. The signals of the first light of the universe were coming up, and they were in the same range, the same type of signals that we have in our microwave ovens. It is exactly the same type, but only the frequency is the important thing and its corresponding characteristic temperature. It is said that it was 2.725 K microwave radiation from space, but that was coming from all directions. We now call it the cosmic microwave background, but now we know that even though it appears fairly uniform from different directions, we can actually find some local fluctuations in many areas, and those are the areas where galaxies and stars were formed. But how did it appear? How did the signal appear? What did they hear really? Or actually they heard it. The signals were converted to corresponding audios, and let us see how it appeared. This is the thing. I hope you can hear it.
Yes, we are here. Yeah, we are hearing you clearly.
Yes. So what happens is, with fluctuations, otherwise you can hear a continuous hissing background. And we did not understand that it is the same thing that we also watch in our televisions, the noise that appears when there is no other signal available for the antenna. And those of us who are from those era when the cable TV was not that prevalent, and it was the antenna that was catching the signals for our televisions, they are more familiar with it. What we saw it in the television screen is exactly the same thing, but we did not realize it, that it is the radiation, it is the historical radiation that we are looking at for the first time. And Penzias and Wilson, they exactly showed it to us. Well, the temperatures were measured, the further details went on for the verification. I'm skipping it a bit because we have to tell a long story. So the cosmic backgrounds are how they formed. It is not important for today. Here, the second development that we were talking about, this is about the detection of exoplanets. And it was first found out at 51 Pegasi, a star. And normally the exoplanets are so far away that you cannot make any optical distinction of them. You cannot see them with even the strongest possible telescopes. So what is the method? The first method that was adopted was that if it was theorized that if there is a heavy planet close to a star, then when that planet will move around the star will also feel the gravitational tug of the planet itself. And as a result, it will sometimes come towards us, and sometimes it will go away from us. And while doing so, it will have changes in its velocity. So its radial component of the velocity can be measured. Radial component, in a sense, if we measure it directly on the same line connecting the star with the Earth, and in that relation, that direction, if we measure the component of the velocity, that's called radial velocity. And if we measure that, then we can find out fluctuations in them. We can also find out that the intensity of the star will also change, because sometimes it is going farther and sometimes it is coming closer. And of course, if we take this spectroscopy of that light from this star, we will find out Doppler shifts in its spectrum. And let us see how the Doppler shift appears there. Please look at the spectrometer line here. You see, when the star is moving, when the star is going far off and coming to us, once it is being red shifted, and once again it is being blue shifted. So here from Earth, we can measure this, and with these measurements using of spectroscopy, we can find out whether there could be a planet or not. But it's still somewhat theorization. You cannot directly see them. You have to make an indirect observation based on data, and that is very much true for black holes. We will come to our discussions accordingly. So when you look for the papers, you can find out that there is also a corresponding intensity drop here, and that dip marks that there is a change, and there is a sharp change of direction. So here comes our detection mechanism. But since I was discussing about the mechanisms and the imaging techniques that already exist, let us just touch upon something which is a matter of the future. I don't like much about talking at a distance. I always prefer to be physically present while discussing all such things, because sometimes I prefer to ask a few questions and take the answers and reactions from audience who are also thinking of the same thing with me. But this time it is not possible, and that is why I miss out this opportunity, because I would have liked to ask you the question, can you guess what this image is representing? And while I do so, in most of the cases, I do not find the right answer, because it's a very difficult thing to guess. This image, though pixelated to a high degree, but it is actually one of the remarkable pictures in astronomy that had been taken just the last year, and it is sun. It is an image of the sun, but now we know the sun so very well, and we have so many good pictures of the sun. What is so special about this sun? This sun is special because it is not the daytime sun that has been pictured here. It is the nighttime sun. How is the nighttime sun pictured or imaged? It is the sun when the sun is on the other side of the earth. So right through the 8,000 miles of rock and stone, we are still getting an image of the sun, because it is not optically constructed. It has been constructed by particles which are always coming through all of us and passing through all of us. Those are called neutrinos. Now, the neutrino imaging has become very, very recent, and neutrino has got something very peculiar. Neutrinos are one of the most antisocial elements, so we can say. They're not social. If you do not call them antisocial, you can at least call them that they do not like to socialize. They don't interact with anyone. If you just stretch your thumb, then every second probably close to 1 billion neutrinos are passing through your thumb. The same way, the neutrinos are always passing from various sources. And it is interesting to mark that when a photon is generated, when a light particle is generated in the sun appears itself as a huge brick wall to that photon, because when the photon tries to come out to the surface of the sun, it has to struggle through, it has to go through innumerable multitude of collisions with various other agents so that it can come to the surface. So it is normally said that there is an average of 30,000 years after the photon is created, and it is actually coming to the surface. And then it takes 8 more seconds to reach out to us. So when we are looking at the light that is coming to us today, we are actually seeing it as it was, or as it was coming almost 30,000 years back. But on the contrary, since neutrinos do not interact almost with anything, they just come out and immediately rush up to us. And hence, if you can take an image with neutrino, then that becomes very, very important, because it gives you the information of the most recent condition of the source. And that is why the neutrino imaging has started in various laboratories of the world. And I'm happy to share with you that even India is building one neutrino observatory. And there are certain other things that I will discuss in today's presentation, of which India is forming a big part. And in many of these technology developments and science developments, we call them mega sciences, India is taking an active role, and India is developing several such laboratories here itself on our land, on our soil. And we expect that in another 5 to 10 years, all of them will be operational. So whoever are listening to this lecture, or probably whoever are students today, they may get an opportunity to work one of them. Well, let us come through all this. What I discussed is the neutrino observatory. If you actually think of go inside the neutrino observatory, it will be somewhat like this: innumerable sensors on the wall, and it is full of water. It is full of water because there are reasons. The neutrino detectors are here shown on the wall, and it always is kept full of water. And normally these neutrino imaging facilities, they are underground, because other disturbances are not wanted, and it is very, very difficult to catch up neutrinos. They do not react very easily, interact very easily, and that is why they are to be developed underground. Now what happens is, this is the schematic structure of the whole thing, how these observatories are and how they work. What happens is, when they come, I mean, the neutrinos swarm into the water mass, they undergo certain changes. I mean, they cause, or rather they excite certain radiations there, and those radiations are called Cherenkov radiations. These Cherenkov radiations, if you ever have any chance to go to any nuclear power plant, which I had once in my life, and not once, in fact, twice in 2 different nuclear power plants, there you can always see where the wasted radiation sticks are kept inside water. There you can see a bluish pattern of radiation all along, and that is Cherenkov radiation. Very interestingly, the Cherenkov radiation is a radiation that can move faster than light. But hold on. Don't we know that light's velocity is the ultimate velocity which cannot be surpassed by anything? Yes, that is very much true. And here also it is true. Here I said velocity of light, but I did not mention the medium. Actually, in any medium, the light's velocity will change. And what we normally say that light's velocity is the ultimate velocity. That is the velocity of light that we observe in vacuum or in air. So when it comes to the velocity, measuring the velocity of light in water, it has to be divided by the refractive index of water, or the medium, whatever we are considering. And once we do so, you can see a small calculation on my screen. You will find out that the velocity will be considerably less than the velocity of light in air. And there can be other radiations which will surpass this velocity, this speed of light, that is optical light, that is measured in water. So it is nothing peculiar, and it is not violating our senses otherwise. Now, let us come to the actual event of 10th April 2019. If you go through, I wish you go through any of the original lectures of Professor Genzel. He is a fantastic teacher as well. And he always mentions that direct imaging of the black hole would be the best proof to show that yes, they exist and they are real. And this is the direct one that we had on 10th April 2019. A lopsided ring of light encircling a dark shadow. Why does it look exactly like that? That we will discuss subsequently. But before going to that, let me tell you that this image was taken by the Event Horizon Telescope that probably you know, and we will discuss about the techniques used in the Event Horizon Telescope after some time. Before that, we discuss other types of technologies and techniques. Now, here is an image of the black hole that was created before the Event Horizon Telescope actually pictured it, and it was created in a movie called Interstellar that you all know. It is called Gargantua, and this movie was perhaps the first possible instance in which, in one movie, one Nobel laureate scientist was actually creating the physics of it. It was done by Kip Thorne, who was also the Nobel laureate of 2017, and he was awarded the Nobel Prize for being instrumental and fundamental in generating another astronomical technique that we know by the name of LIGO detector. So here we go, and here we find what the black holes are. But black holes are not really new, and the idea or the concept is not really new. That is something I want to mention a little, because to understand what are the actual realities and the experimental problems with it, we need to understand it. You all know that if we think of a cannonball and we shoot it right over our head upwards, it will come back. It will come back because of the gravity, and it will go on like that until we can reach the velocity of 11.2 kilometers per second, which we know is the escape velocity for Earth. Now, once we reach that velocity, it goes out. But how far? If the source is bigger, we need a stronger cannon to create a higher velocity so that it can be thrown out. The same way, it was thought even in the 18th century that if you can gather sufficient mass so that the corresponding escape velocity would be 300 million meters per second, then yes, even light cannot escape from that gravitational field. Now, it can appear very normal, but it is not really so. How did it happen? It happened because of a man called John Michell. Now, John Michell is a very interesting character. We have largely forgotten John Michell, but he was a terrific inventor of his period, and we do not know his contributions. We do not remember his contributions right now. If Michell is remembered at all today, it is because of his suggestion in 1760 that earthquakes propagate as elastic waves through the Earth's crust. And that earned Michell the title father of modern seismology. But Michell was also known for many other inventions and discoveries. He was the first man who actually from data found out that there can be double stars. And by observing the double stars, he also created theories by which he could guess that if you can observe the double stars and find out their intensity data, you can find out what are their gravitational interactions, you can measure their masses, you can also find out how gravity works with them. And not only that, along with that, he also said, he developed a mechanism that has been used in astronomy quite a bit later on by observing one rotating object around the other, we can actually find out the data about both of them. Michel was also instrumental in designing, in planning of another instrument with which he was very much influenced by, he was almost contemporary with Newton, and he was very much influenced by Newton's work on gravity. And it is also interesting and instructive to know that Newton worked on gravity during a period when plague was attacking Europe all through, and it was a kind of pandemic. Newton was interested about gravity at his youth, but after trying out to sort out all the problems relating to gravity and the motion of the celestial bodies, he commented in his own diary, it is exceedingly difficult. So he left that. And he was involved with other sort of problems with pure mathematics and sometimes alchemy as well. And then this pandemic sort of thing came, and he was withdrawn to his native place, and there he got back to the gravity once again. And here, with the help of Edmond Halley, in fact, it is almost the instigation of Edmond Halley who made him to write his book Principia, which he was not much willing to write until that time. Now, when he did that, and when his book came out, Michel was very much influenced by the theories of gravity. And what he did is he understood that if you can measure the constant, the universal constant of G, capital G that we mean, you can immediately find out many other actual experimental real data about many other celestial objects. So for that, what he did was he devised one torsion balance with the help of which you can measure the gravitational constant G. But very unfortunately, before he could conduct the experiment, he died. But before he died, he handed over the instrument to another great scientist, Henry Cavendish, and Cavendish just increased the sensitivity of the device, modified it a little, and performed the experiment that we know as the Cavendish experiment for measurement of capital G today. But it was Michel who initiated this whole thing. Now, Michel had this idea, since at that time the idea of light was corpuscular theory, and Newton's corpuscular theory assumed that light too will have influence, will be influenced by gravity. And that is why Michel thought of that if you allow light to come out of a particular object the way a fountain spews water all around, and if you increase the force of the water there, it will go a little farther, but still there would be a boundary beyond which there would be no water. The water will be back to the surface once again. And same thing he assumed will happen for the light, and it will go to a certain extent. And they know the most remarkable thing is they knew that light has got a finite speed, and that is why they could think of that you can think of sufficiently large bodies, he told, bigger suns that will stop even light to pass out of it, and they will appear as black. So he said heavier stars were actually black. It can be possible. That is a remarkable work. But very interesting was the name of his paper. I would like to mention here, and please bear with me. It's a very, very long title of a paper. I have never seen a scientific paper with such a long name. It says, it is Michel's paper, that on the means of discovering the distance, magnitude, etc. of the fixed stars in consequence of the diminution of the velocity of their light, in case such a diminution should be found to take place in any of them, and such other data should be procured from observations as would be further necessary for that purpose. It's huge. But the idea was pretty simple. You just calculate the escape velocity and decide the size accordingly, so you know when it will stop. But it didn't stop there. Michel and Laplace also came out to the same similar idea independently a little later, but they were people of an era where they did not have the right theory for gravity, where they did not have the right theory for light, and hence it did not work. They had to wait for Einstein to come in, and that took almost 1 century. Around 1915, Einstein first started working on the new theories of gravitation. And what he did was remarkable. Before that, Newton always presented gravity as a force. But Einstein thought it's a geometrical construct. It is somewhat like if you have ever seen the trains passing through a bend. It is somewhat like that. The line tells the train how to move. And if you see independently from a distance where you do not know about the existence of the line, you always think that there is some force which is bending it. So a similar idea was coined by Einstein, and he came to this idea depending upon a very interesting thought experiment where he thought that is it possible that if someone is running at a very high speed and increasingly higher speed and reaching out to the speed of light, will the person see that the electromagnetic wave ceases to exist because there will be no movement compared to it? So can there be any frame so special in which the electromagnetism will completely vanish? Apparently, it is an absurd idea. And he said, no, it is not possible. Nature abhors it. Nature prohibits it. And hence, gravity is to be, this whole idea of space and time is to be thought separately. So he changed the construct of the space. He changed the construct of the time, and he found that they're inextricably connected with each other, end-to-end, and developed a new entity called the space-time, which became a geometrical shape. And it is very interesting to find out, as per his proposition, that matter tells space-time how to bend, how to work, how to shape a form, and that shape tells matter how to move. And this mutual connection generated the general theory of relativity later on. And after Einstein developed the general theory of relativity, he landed up in 10 equations which are quite difficult to handle, and even to his prowess, it appeared to be a difficult set of equations to solve. And he thought that without certain simplifying assumptions, it will not be easy to solve them. But there was a man. His name was Karl Schwarzschild. And Schwarzschild was a man who actually was present in one of the seminars in which Einstein presented his ideas. This man was working in army, and he was posted on front, but he was on holiday, and there he could listen to the lecture of Einstein. While coming back, he was so excited, and he was a staunch believer in Einstein's concept. He immediately thought his mathematical ability was fantastic, and he thought that he can make a generalized solution of Einstein's problem, Einstein's equations, and he doesn't have to take any simplifying assumption. And within 2 months of Einstein's discovery of general theory of relativity, Schwarzschild achieved the first solution of Einstein's equation. And when he solved it, he found out that in that equation, there are indications. Actually, he made a very interesting change in the technique of the solution. He himself has described it in this way, that if you try to explain the motion of an aeroplane over an airport before landing, the circular motion with respect to the land coordinate will become quite complex. But if you take a spherically symmetric geometric system and accordingly you change to a spherical coordinate system, immediately the motion becomes extremely easy to deal with. And similarly, he converted Einstein's equation to spherically symmetric coordinate systems, and that is why his solutions became easier. And when he solved them, he found that there is a possibility that there can be elements which become a kind of squeezed up, extremely heavy elements which can land up into situations we call singularity. But at that time, there were guesses, and David Hilbert, the mathematician, he also developed similar theories based on Schwarzschild's work, and he showed here in this image at the bottom, you can find out this is from Hilbert's paper, who showed that if you shine light rays towards such an object, if they directly head on to that over the surface, they will be sucked in. But if they are at some distance, then they can bend and immediately be thrown off to eternity, to infinity, and it will create a shadow here which will appear like a black patch. We will come to it later on. We will find out what actually he was talking about was the consphere, how it is, and he calculated the shadow radius, and he found out that the shadow radius can be 5.2 times the Schwarzschild radius. Well, even though it was a mathematical possibility, even though it was a very much revolutionary idea, no one actually believed in it. The physicists and those practical-minded people, they did not accept it as a reality. Most of them tried to shy off from actually accepting that it is a possibility. But these things changed once again changed with the advent of an Indian, Chandrasekhar, Subramanian Chandrasekhar. And how it is? It started with some observations regarding the brightest star we can see in our sky, Sirius. Some astronomers were following up Sirius, motion of Sirius as a star, and they found out that it is not steady, they orbit. And when they measured it, actually Sirius and Procyon both were under observation. And when they measured it, its actual motions were plotted. It appeared that they are moving under the influence of another thing which is attracting it. The same way we had the idea of double stars earlier. So it was conjectured that there can be a double star, but nothing was visible. And in fact, we did not have a good enough telescope at that time so that it could be absolutely decided what is this phenomenon. What happened is, slowly the telescopes got better, and it was conjectured that there would be a Sirius B. It was called Sirius B. There would be a star Sirius B, which is a companion. But the companion was not visible, and people were not finding it. But then, with better telescopes, it was once found. And once it was found, it was almost astonishing that it appeared to be a very small star, but even then, it was quite heavy to control the star like Sirius. But at that time, the spectrum was not analyzed. The spectrum of that star was analyzed a little later, and it was found that its energy output is quite high. It was described like this: a blazing white star with extremely small volume. And this was not known at that time in astronomy. But slowly we could find out that these white dwarf stars are quite rampant, and they are quite natural, and they are quite frequently lying in many places in the sky. And Chandrasekhar, at the age of 19, when he was traveling from India to England, on the ship, he theorized something, and after reaching out there, he developed two papers in which he showed that if
one star is having a particular having a mass of 1.44 solar mass, then yes, it is possible that below that it will form a white dwarf star. It will squeeze up while the when it is dying, and at the end of its life cycle, it will become a white dwarf star. But this is a limit. What will happen beyond that become a question. And since it was very much revolutionary, Chandra was not accepted by the stalwarts of astronomers at that period of time. And the most famous of them all, Eddington, he even ridiculed Chandra very much. In public meetings, Chandra was heckled by him, even though otherwise at other times he was even checking out some calculations by Chandra. But somehow, so much was their resistance of mind towards formation of such extremely heavy small stars, they could not accept it. But Chandra in particular, he explained this whole scenario by mixing up relativity with quantum mechanics. And he showed that when the stars will become so much squeezed, the electron degeneracy, the electrons have a special character that they do not allow the same level of quantum numbers to two different electrons. It cannot happen. It's called Pauli exclusion principle. Many of you are probably aware about it. And because of that, if you try to squeeze off electrons within a very small volume, they refuse to go beyond a certain structure unless the force is enormous. And with the kind of masses that were observed about the white dwarfs, it was not possible to squeeze them up any further. And that is why this pressure that is generated because of the mutual repulsions of these electrons generating of the exposure to the, it is called the degeneracy pressure, and that degeneracy pressure could hold on the gravitational collapse. That but the natural question that generated out of it was, is it possible that if there are more mass into the star and it can even up, it can even break the electron degeneracy, can something else happen? And yes, very soon other scientists could show, yes, that is also a possibility. If the gravity is much more, in that case, the electron degeneracy will not be able to stop gravitational collapse, and the electrons will mix up with the protons, and everything will settle down as a very big nucleus of an atom, and everything will be neutron only, because the protons, when they mix up, when they coalesce with electrons, they will form neutrons, and this will become a hugely dense object, a very compact object, but a very small object called the neutron star. But even then, when these things were in discussion, they were not sure that it can be real at all, whether this can be found out. But subsequently, whatever is the case, through different sort of heckling, through multiple resistances, Chandra continued with his ideas, and so did a few other scientists. I'm skipping out all those stories because that will take almost a whole day to deal with. And ultimately, it came down to a scenario when people were more or less convinced that yes, there can be black holes, but even then, those black holes were considered to be rare, and it was considered that probably they will not be very meaningful in the formation of this universe till another decade or so, when further developments in this field happen. And one very important scientist in this whole scenario became Roy Kerr, who could show that there would be rotations in the black holes as well. And here we must mention that one of the Indian scientists there did some remarkable job, and that is Omar Kumar Chaudhuri. He developed, in a way, it was not a direct collaboration. He independently did it, and Lev Landau also worked on it. So they worked out an equation called the Raychaudhuri-Landau equation, and depending upon which it could be shown that the gravitational collapse to a black hole is a natural consequence of relativity itself. And that was pretty remarkable. Here I would like to tell something about the black hole's character that was particularly mentioned by Wheeler. Wheeler said that the matter of the core pours torrentially inward from all directions like 1,000 Niagara Falls on its way down from the original stellar dimensions to ever smaller sizes. In 1968, he mentioned this and said in less than a tenth of a second, the collapse goes to completion and little, if anything, is seen. Case by case led the relativists to one undeniable conclusion thereon. No matter what a star looks like before its gravitational collapse, all its distinguishing features vanish, leaving behind only 3 pieces of information connecting to a black hole-like structure. The only properties that remain are the former star's mass, its spin, and its electrical charge, though that charge would likely be neutralized after attracting equal and opposite charges from its environment. And John Wheeler also said, a black hole has no hair. This became a very famous statement because it doesn't have any frill. It will only be described by 3 parameters. No defining characteristic that makes it look different from any other black hole. There is no way to tell from outside whether a black hole was created using neutrinos or electrons or protons or old grand pianos. That is what Wheeler wrote. Or if it had been yellow, wrinkled, or polka dotted, a black hole is a black hole is a black hole. Every distinctive feature of a star disappears behind its inscrutable event horizon. The gravitationally collapsed object should not be thought of as a frozen star at all. Instead, it should be thought of as a soap bubble, like pure gravitational field. Its only properties being mass, angular momentum, and electrical charge. The singularity itself would never be seen, forever cloaked behind the event horizon. That was the scenario when Roger Penrose came into the picture. And initially, Penrose admitted that he did not have much idea about the black hole, but he got interested. That an object of so cosmic importance could appear so basic and described by mere 3 numbers was simply flabbergasting to everyone. Penrose was trained in mathematics, and Penrose first became interested in the relativistic singularities after hearing Finkelstein lecture in late 1950s in London. And he said, when I got back to Cambridge, knowing very little about general relativity, I started to try and prove that singularities were inevitable. It seemed to me that maybe this was a general feature, and that is the thing which has been acknowledged by the Nobel Committee right now, and they have said it is his biggest contribution. Yet, at the same time, they also seemed to him a bit ridiculous and mysterious. These terms were exactly used by him, ridiculous and mysterious. After intermittently work on the problem over the ensuing years, he at last published a theorem in Physical Review Letters in 1965 that has been called by some as the most influential development in general relativity in the 50 years since Einstein founded the theory. And this was actually an extension of the Landau-Raychaudhuri equation. And that has been acknowledged by the Nobel Committee this year for the theoretical construct. We will come to its experimental viewpoints. But before that, once again, salute to this man. And it is never a good idea, probably, to bet against this man at all, because so many things he predicted that came out to be true. But before we get into the experimental viewpoint of it, we need to take a note of one phenomenon. We know about such compact objects at a very huge scale, and we know about such compact objects at a rather smaller scale, but nothing intermediate. We know about supermassive black holes. We know about stellar black holes forming out of the stars. But in between, there is a huge gap. At least very recently, up till very recently, it was so. But very recently, there have been some report that some intermediary black hole could be found out, whose details are yet to come out in every possible way. So we have to wait. Now, we do not really know how supermassive black holes are getting formed, but now we know that these supermassive black holes exist, and it started once again in 1963 when the quasars were discovered. From the quasars, the new interests in supermassive black holes started. And what it is, today we are not discussing Hawking, but I sincerely believe that had Hawking been alive, he could have been awarded the Nobel Prize as well with Roger Penrose, perhaps. And he said the event horizon, the boundary of the black hole, is like the edge of a shadow, the shadow of impending doom. It is a literal statement, but there is some truth in it. We'll go to it. I'm not going into the detail of anatomical structure of black hole today, but even then we will need some ideas of what is called accretion disk, where the materials they circle around the black hole. The event horizon, the last point beyond which we do not know what physical rules are governing them, and at the center of it is the singularity, where everything collapses, and this is the last line of light which are bending and going towards infinity. Otherwise we call it photon sphere, and the innermost stable orbit in which matter can safely stand behind the sturdy rails of the Niagara almost. Well, let us see from the Event Horizon Telescope experts what they thought of it when they actually tried to find it out. Professor Genzel time and again has mentioned in many of his lectures that direct measurement would be the best thing to do. In a while, very soon, we will discuss what are the other options. When he first time started working, he started working with Charles Townsend, the man who got the Nobel Prize for the discovery of measures. And in his second incarnation, Townsend got interested about astronomy, and he started a procedure by which he wanted to measure the velocity of the gas that exists around the galactic center. And in that group, Professor Genzel is working, and by creating methods to measure the velocity of those gases, they wanted to show that there is some super heavy and compact object existing at the center. But let us see what the Event Horizon people. I expected the Event Horizon people also to get the Nobel Prize, but somehow it did not happen. But anytime probably it will happen as well. Let us see what they thought to find out and what they think about the black holes.
Black holes are the most exotic and extreme manifestation of Einstein's theory of gravity, general relativity.
It's when matter gets to be in such a small space and is so dense that the force of gravity prevents the light from escaping.
They're quite literally what you think of when you hear the word black hole, something into which stuff goes and never returns. Once it passes the event horizon, that is of no return. It's gone from our universe forever.
Everything is locked inside the black hole and nothing can escape. So we don't get any information from within this very compact object.
And even time slows down and comes to a standstill at the edge of the black hole. That's one of the weirdest and most exotic objects we can imagine.
Black holes are also the engines that power the most extreme events in astronomy.
We know they sit at the hearts of galaxies and they drive
how those galaxies grow and how those galaxies die. They swallow gas and stars up. Enigmatic and mysterious objects that live at the boundary between our two great theories of physics, general relativity, which describes gravity, and quantum mechanics, which describes the smallest things in the world.
Some kind of rent or tear maybe in space-time, and a place where we don't understand the physics and have a lot of serious questions. There's a very peculiar kind of object in the universe, and we would like to understand it.
We can study.
Well, let us get to the next level. Here we point our interest towards this Sagittarius A star or Sagittarius star, to be precise. What is the real point of interest right now? Because people guessed that there must be something very heavy and very compact out there. And in 1960s, this whole thing started when they had a renewed interest about finding out such compact objects. Now, this is the center of our Milky Way. And if we look at this region, you can find out patches of black areas. And you can very easily understand that these are black because optical signals from those regions are not reaching out to us. They are full of dust. And it is extremely difficult to image something residing in that region, really. There are no other methods to, and there are no optical methods to directly image them. And we have to think of alternative means. So how do you prove that there is something very compact and something heavy? And Professor Andrea Ghez says, by showing that there is plenty of mass inside a small volume, showing that the mass is within its Schwarzschild radius. But even that, how do you do that here? And both the teams of Professor Genzel and Professor Ghez, they created a method by which they can focus their attention to a cluster of stars which are close to this galactic center. Now, these cluster of stars, what do they do? If you can find out this cluster of stars, if you can image them, and then if you can observe them over a period of time and perform a kind of Keplerian experiment so that you can construct and reconstruct their orbits, you can prove that there might be a point of attraction. And by measuring the parameters of these orbits, you can probably say that how strong gravitationally that object is, which can also show what is the volume of it and what is the mass of it. And in doing so, you can prove the existence of this compact object. And what is the kind of speeds of them that are expected? It is expected that this number on your screen, it is the speed, that miles per hour, and that would be 3% of the velocity of light of a particular star that has actually been measured and data has been taken. So you can understand how big it is and how accurate it has to be to prove the existence of all that. And they were excited about an observation of last May when they could actually find out two positions of the star. But how does it look like? What do you find? On the left, you can find animations of 20 movement of those stars. And if you observe them, you can find out that they are rotating. And one of them close to the center is getting a very heavy turn coming to a particular point. And this has been refined and refined to the animation on the right. And here the stars are also identified. Their orbits are properly planned, and you think of what they actually got into. This is the result. This is the result of the experiment. Both it is separately did. But what was the difference? I will do that very soon. This is Professor Genzel, and Professor Genzel observed that since optical imaging was not possible, it is probably has to be in the radio range, which can penetrate through the cloud of dust. And that is why his group tried the radio imaging of the cluster of stars, whereas Professor Gazer's team, they tried the higher range observation and higher imaging of those cluster of stars. But even then, it was not enough, because it will need something else. To resolve these stars accurately, we have a big problem which exists in our atmosphere itself. But prior to that, Professor Genzel always prefers to mention that 1960 was the beginning of his interest about this whole thing, when Martin Schmidt actually found out that there's something called 3C273, and it's a quasar, and with that quasar they could find out that these are very bright and old galactic centers, but they're exceedingly far off, and measuring something at that center would be very, very difficult. So they had to think of something close by, and yes, we have a galactic center which is 26,000 light years away, and that is why their interest came to our galactic center. But in that galactic center, when they tried to measure the biggest possible terrestrial observation problems were the atmospheric movements. The atmosphere always has got a turbulence, and that is why they had to develop one. Not to develop, it was developed earlier by the military, but they refined it and adopted it. It is called adaptive optics. Now here you can see the image of Neptune. This is the image of Neptune on your right, which was taken by Hubble Space Telescope. On the left, this is the image that has been taken terrestrially with the help of adaptive optics. And of course, at the center, this is the Voyager image of the Neptune. Now, this has no comparison, because when Voyager took it, it was pretty close to the actual object. Let us move it, let us remove it. And then you can compare these two objects to find out that here is considerably larger resolution and much better detail in this image than could we collect from even the Hubble Space Telescope, which is one of our biggest prides. But what is that? What is this adaptive technology? Well, this is the thing that they had to measure. These are the streams of gases, and initially I told you that Townsend was trying to measure these gas velocities. They did so actually, but Professor Genzel always mentions that you can always think of 10 other scenarios where the gas movement will not be able to explain that there can be one very strong object. I mean, there can be a very massive compact object. Now, this is the massive compact object they were projecting and they were looking for, and for that they adopted this adaptive optics in the VLT by ESO, Very Large Telescope. I just included this picture to show how these observatories look like. But one remarkable phenomenon of these observatories is if you see the nighttime pictures of these observatories, you will find out a very strong laser beam coming out of the observatory and pointing towards the sky. What it is the actual invention and that helped them to do this. What is the idea? The idea is this, perhaps assume that this is the atmospheric layer, and the atmospheric layer always generates turbulence, and since its refractive index changes with its density, hence the light ray that is coming through it will always have a shift. It will be flickering, and the basic idea is to take the twinkle out of this star. And how is that possible? For that, they identified that about 90 kilometers above the ground, there is one layer in the mesosphere of atmosphere, which we can call the sodium fluorescence layer, in which if we can pass through one particular sodium laser beam, then that can excite some sort of fluorescence in this layer, and here we can create one artificial star. Now, if we can create it here, then this point will shift with the turbulence of the atmosphere. What the people do is This beam is pointed towards one terrestrial point or observation point that is called guide star, and this guide star is considered very close to the actual observation target. And once you do that, you will have one corresponding artificial star here, which is observed by the telescope. So what is happening is this signal is coming, and with the help of the movements in this artificial star, the system can actually calculate how much the light ray is shifting, and accordingly there is a negative movement that is created inside created inside the system, and that is imparted to a deformity, regulated deformity in the mirror. These are deformable mirrors, which are the ultimate mirrors that creates the imagery. I will give you one animated picture so that you can understand it better. And that gives us the stable image mix. So let us into it and let us see how it works. This is the normal scenario where the star is flickering, but now we apply adaptive optics, and let us see what adaptive optics is. Here is the laser beam coming out, going to the sodium layer. It is at this distance, and here the flickers are being created in that artificial star, and that is your guide star. And as a result, this signal from the guide star is coming here, a negative feedback is created, and accordingly the mirror that is being moved and deformed so that the movement of the light beam that is being received here can be compensated. The mirror surface here is flexible, and it is being actuated by several magnets so that it can be deformed in different positions, and it is very calculation intensive. It can accordingly create the most stable image of the star, so that now we know this is the exact scenario. And with the help of it, once you can clearly decide about the object's position, you can track its object. This is Professor Andrea Ghez, and I have already told you that while Professor Genzel tried the radio waves, Andrea Ghez tried to measure the IR scenario. And here is an image of young Andrea Ghez. This is an image she likes, and she wanted to show that she wanted to be the first woman on the moon, but ultimately she reached the galactic center instead. And here is the declaration of the first woman in the space that she is reading here. But what they found out is actually a three-dimensional problem. The cluster that they were pointing to, they have refined and published very recently the actual movements in proper dimension. I would like to share it with you. Well, with this image, you can understand how difficult it is to follow them up, because they are so densely clustered and such a difficult thing here. And now you have to plan the orbit according, you have to plot the orbit, and it takes about 16 years. So it is almost the lifetime of an active scientist, or at least the half of it probably, but it has to be correct in the form of gravitational structures. So that is what they did, and these are the 2 points that they measured and got excited about very recently. And there are some other developments regarding the imaging as well. I'll just finally describe the way the VLBI, or the Very Large Base Interferometer, tried to image the black hole, and then we'll come to the end of our presentation. I'll just briefly describe what it is, because both Professor Genzel and Professor Genzel, they think that the ultimate proof of the compact object would be through VLBI only. And let us see what it is. It is somewhat like, but that can be understood through a duck analogy. Suppose you have a set of ducks roaming around in a pond. What will happen is each duck will generate their ripples, and those ripples will interact, and standing at the edge of the pond, you can measure those ripples, and let us see how they can help us. Suppose this group, if they are compact, they will have one particular pattern of ripples. If they are distributed, the pattern of ripples will change accordingly. And when at this edge we are standing here, we can find out how the pattern would change. We can measure the parameters, how disturbed it is getting by the amplitude, and what is the coherence length, that's where same type of amplitude is being repeated. And once we measure these data, out of which we can construct the distribution of these ducts and how they are placed there. How the elements are placed there. And this is the method that is used in large base interferometry. It is not a direct imaging. It is not just a click and shot type of thing. It is actually a data reconstruction of the whole thing that you see. So what you see as the black hole, as the image of the black today, is not the image, it is a data reconstruction. And it is almost like listening to the music. I'll just give you a small experiment. Suppose you have you listen to some frequencies discretely. You cannot judge a song, but when many of them and more frequencies are added up into this string, then you can understand how it is forming a whole song, and probably you will be able to identify the song itself. So it's changing slowly. More frequencies are coming in, more data is coming in, and you can construct the whole song. Well, this can generate into partial images, and that is why what they did is they tried to create one simulated model and match the actual model with them. And the imaging was firstly tried in our galactic center, but because certain measuramental parameters, that was not possible. Since I understand that I have been quite a long time, I'll skip a few things. I would only like to show the photon sphere animation, that the reason of the image, why it is so. Suppose the photons are rotating around the axis like this. If we see sideways, they act like that. Now, if we see head on, we will see shadow inside, and that is why the image is formed in the exact form as it appears to us in the simulation. Well, the direct imaging has been possible. Probably we'll refine it. Probably we'll have more measurements, and for doing so, a worldwide telescope was created by using multiple radio telescopes at different parts of the world. Their reasons can also be explained, and how it was reconstructed. There are algorithms working in it, and this is the computer scientist who led one group of the computer algorithm that created it. I'm not getting into the details of all these. I'd only like to mention that in separating areas, separate data were collected in separate regions of those radio telescopes, and with them the timestamps were created, and finally they were compiled, and it is a huge computational exercise as well, and that is how the technologies mix up and generate the ultimate image. I'll just show one last pattern, how these images were formed with collection of more data, and as the earth was rotating, more and more telescopes were coming into play, and their bases were connected, and accordingly corresponding data was being collected, and the image was being modified accordingly, and final figure generated out of such data accumulation over a very large period. Well, more or less, that is how direct experimental observation of black holes. We come to the end of it with the understanding. I would like to quote from two of my favorite astronomy presenters. One is Carl Sagan, who said, "The universe seems neither benign nor hostile, merely indifferent." And we have seen that the universe doesn't care whether we believe that black holes can exist or not. It just creates certain things the way it likes to. And Neil deGrasse Tyson mentions another thing that is very philosophical, and he says, we are part of this universe, we are in this universe, but perhaps more important than both of these facts is that the universe is in us, and this curiosity continues. We'll keep on collecting data, we'll keep on constructing more theories, we'll try to find out how actually it works. Thank you very much.
Thank you, Manas Bharisha. Really, we are traveling along with you, and we are walking along with Esco. When you started this journey of showering of knowledge from the beginning of the radio signals that Wicked Bell Institute, and later the contributions of all the scientists, when we start from the Michel's contributions and these equations, then we come to the Schwarzschild, and later we are proud with this Subramanian Chandrasekhar and his ridiculous remarks later become regarded well. And you go through all these scientists, Royker and J. Wheel and these things, and analyzed all the aspects of the present black hole theories and its all these aspects. And we are so proud to hear from your part. And you analyze, you move in a way, and the way you express, you explain the optic adaptation and interferometry is also very, which was so explanatory and so understandable to even to the school children, and we realized that it is very great opportunity we received from your part to know about these things. And you started the journey in a scientific way, and you ended in a philosophical mode, and that's the word of this type, that universe, and we are with the universe, and we are all children. I feel as a children, as a child, to see that your words, and we are in search of these more clarification from you also, and our students are waiting here to interact with you to make more clarifications. We give you a big thank you, sir.
Thank you very much. It is all my pleasure. Thank you. Thank you very much.
Thank you, sir. Then before we go to the Q&A session, and I want to get some reflection from our EKTP sir.
Sure.
Welcome, sir.
Thank you, Shajil Mash. It has been an exciting scholarly talk that we had the benefit of spending this afternoon. Excellent talk. And in fact, our students, curiosity in space is largely in black hole. I have seen whenever you have a space camp or a talk related to astronomy, astrophysics, space, etc., questions from students, school students, will be largely in front of black hole. So today's been a feast for them, from Mr. Manush Bakshi, and I am extremely grateful to you, sir, for coming and spending such a very nice time with us. And
Thank you,
I
sir. Thank
recall,
you.
I recall my, I have been known to you ever since you landed Kozhikode and took over the position, and you have uh, greeted me with folded hands every time when I walk to your office. And likewise, this time when I called up requesting you for giving a talk, you very graciously accepted it, as Shadil Marsh said in the beginning itself. So it's something
Always with
very
you.
nice,
Always.
very nice thing. And a scholarly person of uh, your ilk is something very difficult to meet. And we are very Calicut people are actually very blessed. Students in Calicut are blessed, but unfortunately the epidemic is not allowing students to come to your place. That is a very unfortunate thing. And we are embarking on this kind of thing to combat that problem. In fact, I recall from February 8th and 9th, we had planned a space camp in Calicut, and Manush Bhakti sir very readily extended whatever support needed for that. But unfortunately, the signals of COVID began by three students from Wuhan coming here, and then PJ Butt, who is already listening to us here, he had booked his ticket from Bangalore to come here. He called me and said, "Kuti, I hear it something like this. Is it an appropriate time to do it?" So we had to cancel it. So ever since that, we have not been able to meet. You are in your talk also. You are saying that this is not a real thing. That when you talk, face to face only, it becomes really a realistic feeling. Anyway, we are not able to bring it out. So I'm very extremely thankful, sir, for this thing. And students are waiting. I don't want to be between you and students as a stumbling block. So let us open the forum for students. Shadil Marsh, please take over.
Okay, thank you, sir. We totally agree with your comments, and it's very timely and very appropriate. And before that, we want to get a few words from PJ, but he's also continuously supporting in this program. PJ, but sir, please join me for a moment. But sir?
Yes.
Okay, sir. PJ, but sir?
Okay. Please.
Yes, sir.
Sorry, I'm not able to switch on my camera. There's some problem here, but I hope you are able to hear me.
Yes, sir. We are hearing you. Okay.
First of all, let me express my thanks to UL Space Club and especially Dr. Bhagaji, I think, for an excellent talk, sir. It was so informative, and we are all, awed by this Nobel Prize on related to black holes. And I also agree with Kuti, sir. Whenever I have interacted with the students of UL Space Club at several times, every time I have seen their great interest in these kind of aspects. Even in our group called WhatsApp Bayakasha group, the discussion goes on mostly on black holes when it comes to astronomy. So it is I was very curious to listen to this lecture. It was such a fantastic talk, giving so much of information, sir, right from the days of Einstein, and you covered almost every aspect of it. And so nice of you that you covered about the contribution from India also with respect to this particular effort. And I am in fact today I have become enriched my knowledge with respect to this topic. Thanks to Space Club for this, I am also agreeing to Kuti sir. We are waiting for the end of this pandemic so that we will come face to face and we'll be able to interact with all these bright students of this particular Space Club.
Thank you for your kind words and reflection on this program. And without wasting any time, we the question and answer session, which means that we ask questions. And I invite Bharat and Arjun and Sriram, the PPs in the Q&A questions. And I invite Bhakti also to place these questions and explanations.
Thank you, Shajil sir. I hope I am.
Yes, yes,
And
yes, oh, yes, yes. You continue.
first of all, extremely grateful to Maharaj sir because we've previously been able to see him and interact with him physically. So it is kind of different to be interacting with him online, and the kind of feeling that you get when you interact with him in personal, in physically is something else. Uh, in fact, great understanding of this particular knowledge is indeed needed for talking a topic like black holes. And the most important thing all of us know is that Mansi Bagchi sir is someone who has a great deal of knowledge, not just on black holes, but on all aspects of astronomy as a whole. So, black holes are in fact very intriguing topics and something that all students like me are very much interested in. And it is very much from the number of questions that has come up in the chat box. Just comment to you, right? So the first question, let me please decide, has been from Sajina Santosh. And the question is, how do scientists calculate the mass of a supermassive black hole?
Your voice is dropping. Actually, I'm not being able to understand the question.
Okay, sir. Okay, sir. Can you please mute your mics for a moment?
Sure.
I think I am audible right now. Okay, sir. So the first question is from Sajina Santosh, and the question is that, sir, how do scientists calculate the mass of a supermassive black hole?
Well, it's a very simple Keplerian calculation. Once you can identify the orbit of one star, and you know the mass of that star from other means and other observations, then it is like calculations you apply for this planetary system and solar system. It is the same way. Then the calculation is nothing very difficult. It is only the observation part, experimental part, that is the real challenge here. After that, it is a normal, simple Keplerian calculation, just Kepler equations.
Okay, sir. So the next question is short. So the question is, so we can create black hole bombs in many ways to extract energy from it, such as sending electromagnetic waves or dropping asteroids and receiving more energy back and all sorts of things. So if we have all the technology, and yeah, it is kind of futuristic, if we have all the technologies and if it is all possible with the technologies that we have, which of these methods would be the best and which would we choose?
Frankly speaking, I have no clue. I never studied such things, so I'm not really a competent person to comment on that.
Okay, sir. Can you please wait for a moment? Okay, so the next question is also important. It is asked, so how stable are rotating black holes and this space-time around such black holes? Oh, let me please repeat it. How stable are rotating black holes and how stable are the space-time surrounding such black holes? So your mic is muted, sir.
There are theories about car rotating black holes under certain perturbations and perturbing conditions, and yes, they can be stable.
Sir, can you please wait for a moment, sir? I think there is a little bit of a technical glitch here with the organizers. There has been, in fact, plenty of questions that has been asked, and it is kind of difficult to even be selecting a few of them. So please do pardon me for a moment. So the next question is from Abhiram TP, and he's asked something like, is the
Einstein's equation of mass energy equivalence, E equals mc square, applicable when you speak of things like black holes? Because whenever we speak of black holes, the first thing we say is that the physics that we know infinity, and there is all these critical things going on. So are these kinds of things that we think are true applicable?
Well, my suggestion in this regard is, please do not go by the black hole myths. Try to read the books by the scientists and not the popular science books. Popular science does not give a proper representation of the black holes. So please form your ideas from the books written by the scientists. And I suggest that the book on black holes by Kip Thorne is an excellent guideline.
Thank you, sir. The next question is also from Abhiram, and he's asked, could black holes be used as an energy source?
The black holes generate huge amount of energy when they suck in materials into it. Well, as of now, I do not know of any technique or any technology that can extract it to other purposes.
Next, I would like to invite our dear brother Varunatan to please come forward and have a comment on this beautiful session and ask any questions if he has. Varun?
Yes, Bharat. Thank you for inviting me, Bharat. And sir, it's quite interesting about people are saying about the reality of black hole, and still some people believes that the black hole is a hypothesis, even though we have captured the picture of a black hole using Event Horizon Telescope. And what would you like to say to those guys who doesn't believe in black hole and are still believing it as an hypothesis? And I also want to know that what's the most difficult thing that Event Horizon Telescope has faced in the capturing of a black hole? As we all know, it's completely a difficult thing, but I just want to know what was the most difficult step in that process.
Two parts of your questions. The first one you asked about was, I've just forgotten. Could you please repeat it once more?
Sir, most of the students and most of the many of the scientists believe that still it's an hypothesis.
Yes, regarding the hypothesis. Yes, I understood. I remember. Let me tell you one thing. It's a very interesting cue from the statement of the Nobel Committee in their citation. In their citation, they have not mentioned black hole at all. They have mentioned about the existence of a compact object. So, as Professor Genzel likes to place it, that, well, it is better to be correct in this way, that it is proving the existence of a compact object and massive compact object in that region, which is very, very likely and most likely to be a black hole. Now we more or less are certain that yes, these things are there and these things exist. But there might be a few issues still, but ones who used to say that nothing such is real, that is completely ruled out. It is absolutely not so. Now we know they are real. Now we know that yes, those things exist. And one more point, let me explain that initially people used to say that since it will require a huge density, nothing such can exist ever. But a very interesting thing is, if you can fill out a volume of our solar system with water, then that will become a black hole, because it will become such massive that will act as the black hole. So it is not necessary that they have to be super dense. Otherwise, Well, close to the core, it is a different concept altogether, and we do not yet know how matter behaves there. But otherwise, from outside, if the mass of water even to the size of solar system can be collected together, that can behave as a black hole. So it is not necessary that infinite density is to be formed. And that is why most of those points on which the non-believers used to talk about, those are ruled out. And it is very, very likely that yes, they are black holes. And secondly, you asked another question. What was that?
Sir, we know that all the steps in the capturing of the black.
What is the most difficult? What
Yes.
was the most difficult thing?
Yes, sir.
In fact, so far I heard about their project reports and all. I found that they considered initially the creation of such a huge telescope that has to cover the whole diameter of the Earth a very, very difficult concept. Secondly, the algorithm development, that as the Earth rotates and new dynamic changes in the base of the interferometer is coming up, and accordingly you have to take data. I mean, I do not find anything less difficult or most difficult. It is almost all throughout, everywhere it was a very, very challenging concept. And even now, resolution is a very important issue, because the kind of device they had, with that our galactic center could not be measured, could not be imaged. They used M87, and they are waiting for more resolution with inclusion of further more radio telescopes. In fact, one has to come up in India as well. So they are looking for another 5 to 10 years, probably, insertion of more radio telescopes, and they are expecting more resolution so that even other galactic centers can be imaged. I think currently that is the challenge. And another point they mentioned in their project report was that they wanted to have a video, but that could not be possible. It could only have a, but I mean, the time dynamics was not included in the image that they could form. Probably they would like to include the time dynamics.
Yes, sir. Thank you for answering my question, and I think it's, the time is up now. We have just reached 4:55, so I requested to Bharat to continue. Bharat.
Thank you, Varunata. Thank you, Manish Bhakti sir. I think let us conclude with the final question of today's Q&A session. So I would like to add a little bit on what Varunatan said. So he said that a lot of people still don't believe that black holes do exist. And there are plenty of speculations and theories saying that there may be some other things that could exist instead of what you call black holes. Like when Stephen Hawking worked alongside Roger Penrose, and then he wanted to prove that black holes and singularities do exist. And then all of a sudden, towards the end of his life, he wanted to prove that black holes don't exist. And then there are crazy speculations, like there is something called a cosmic firewall which prevents something to enter a black hole. And then you had to find solutions to the information paradox, and plenty of different things are there. So, sir, how do you comment on the other, some other ideas and theories that exist which could otherwise rule out black holes?
Keep my fingers crossed, and I always suggest everyone, please read only which are peer-reviewed reports and nothing else. Popular science doesn't make good science at all.
Thank you, sir. That was exactly the kind of answer that we all expected. Thank you so much for speaking with us. It was a great time to be interacting with you. Over to Shajit sir for the vote of thanks.
No, thank you, Bharat and Manish Bhakti sir. Hello.
Yeah, thank you.
Okay, thank you, sir. And the way you reacted to the questions and you entered the questions also, and that means that the students should go so much fundamental science. They have to grow with the fundamentals. Then they can think and they can imagine and they can grow with the philosophy also. That's a message you have given, I think so. And we maintained the same energy when we started with 2:45 here, and we are now into around 5 o'clock now. We are maintaining the same energy with the students and our proud presenter, Manas Bhakti sir. We are ever thankful to you. Next, we come to the concluding session. That's the vote of thanks. And we are happy to see that some our planetarium people are here. Sunil sir and Binoy sir is there, and they are with us. And I want a few words from Sunil sir also on this program, sir. Welcome, sir. Sunil sir, please come.
Sure, sir. Can I excuse me for 1 minute?
No,
Please, sir.
one second. Wait there. I invite Sunil sir. Please come, sir. Okay. Sunil sir. I think Sunil sir. Okay. I think there is a connectivity problem there with Sunil sir.
Sunil has left the meeting.
Okay.
Sunil has left.
Next we
Vinod is there.
Yes, we have to hear some few words from Varun. That I think he's speaking about the US Space Club. Okay,
sir, I am here.
Okay, welcome. You speak.
Shakil sir, it was a wonderful program. Actually, it was a wonderful program. Students also interacted well with our PC. So it was a very nice program. We all enjoyed it. Thank you for it. Thank you.
Shajil Mash, just one interruption. Kindly allow me for a minute only. We our usual thing about announcing the quiz result has to be done before the vote of thanks. And also an announcement about the forthcoming quiz today, right now also. Varun, why don't you handle that?
Yes, sir. That's why I just interrupted the. So we will announce winners of the last week quiz. In fact, not the last week, the last space quiz of US Space Club of the session by Dr. Rajaram Nityananda. So we will announce the name of the winners through our all social media platforms and our WhatsApp groups. And the link of today's quiz will be posted by our student fellow Adil Krishna in the chat window, and we will also post the link in our social media accounts also. Adil, I request you to post the link for today's quiz in the chat window, and you can refer after. You can go to the link after the webinar ends. So attend the quiz. I request all participants to attend the quiz as fast as they can. The fastest and the accurate answer will be the winner. So that's also the last week quiz winners will be announced at our social media platforms and will be shared through our WhatsApp groups.
Okay, thank you, Varun. Now I think we are going to conclude these things, and before that, we have to declare that on the 7th of this month, the webinar will be there, and that will be from part of the biotechnology field, and an eminent scientist from Rajiv Gandhi Center for Biotechnology, Dr. Sonia, is presenting, and she's the first. I think she's the first lady coming to our webinar series, and we are eagerly waiting for that. And Kuti sir, sir. Yes. Is there anything more to be added there, sir?
No. You please carry on. Nothing more from my side. Thank you. Please go on. Please go on.
Thank you, sir. Then I invite Febin Firshad to make the vote of thanks session here. Febin Firshad is a student who's actively participating in the US Space Club, and he's so curious. He's continuously asking questions. He's a familiar face to all the science community and this webinar series. Welcome, Febin, to express the vote of thanks on behalf of this US Space Club.
Thank you, Shajil sir. And is my voice audible?
Yes.
Okay, and good afternoon, everybody. We are here in this platform for more than 23 weeks, and the energy and enthusiasm of all webinars have been coming up. And of course, talking about black holes, their energy sums up to the maximum, and it's expressed in their questions also. This program is by UL Space Club, an initiative of ULCCS Foundation, and we are proud to have an eminent scientist such as Manas Bagji sir, and I have heard a lot from him, and every classes had a sack of knowledge as well as enthusiasm. Presence of you all are the energy and inspiration for us to conduct more and more on behalf of UL Space Club. On behalf of UL Space Club, I extend my sincere gratitude towards Manas Bagji sir for the brilliant and informative session which aroused our interest and imagination into it. And many eminent scientists, including many scientists, engineers, professors are our usual viewers, which makes us proud. And happily, I thank all of them and expect their further cooperation. I thank all the student participants. I must express my hearty thanks to Kutti sir, our all in all of UL Space Club. Kutti sir, Jairam sir, and Sejil sir have been working, and many more have been working restlessly for the nurturing of the students with interest. I extend my sincere gratitude to them, and I thank all the coordinators, Master Sriram, Master Varun, Master Bharat, and Master Adil. And once more, I thank you all. Wish the good to all.
Okay. Thank you, Will, for your expressions of gratitude. And now we conclude, and we will meet again on the 7th of this month with a new topic that will be informed through our broadcast or WhatsApp group. And a big thank to our great Bhagis are the proud of our whole code and career.
Thank you. The pleasure is all mine. Thank you very much. Thanks for calling me.
So nice of you, sir. So nice of you. And
Thank
what's
you.
up?
I'm grateful to you all.
So nice. We had an excellent day today. Excellent day.
Excellent.